Morning, folks. Y'all doing okay this morning? Yeah? Excited to be here? Where are all the athletic training majors last week? Did y'all have something going on? Did y'all get together and decide you weren't going to come to class? Was it something going on, like with school? What, can I ask what went on?
It's just like an athletic major, very different levels.
Okay. Don't forget we're going to have a quiz at the end of class today. And going to move on with electricity. Let's go ahead and pick up where we left off. So we were on power last time. To sort of recap this, power, remember, is related to both the voltage and the current. And electricians use this a lot more in the amount of current that they might have in a household circuit, for example. And so we worked a simple problem where you had a 60-watt bulb and a 120-volt power supply, which is what you have in your house. And so a light bulb like that would draw about a half amp current. So, for example, if you're designing a house or some other building with a circuit in it, you can't have too much current in a particular circuit because it can burn up wires, cause fires, or whatever. So they put in systems with circuit breakers, which you've seen, I'm sure, circuit breakers. Yeah, those circuit breakers will kick off after you get a certain amount of current, usually about 15 or 20 amps. And so, for example, if you were to put in 30 of these light bulbs, these 60-watt light bulbs, then that would probably kick the circuit breaker because you would exceed the maximum amount of current allowed. So that's power. You could have some simple calculations on the exam, which is, remember it's on May, whatever that date was. Anybody know right off? It's on the syllabus, but that's going to be your exam number 4. All right. We're going to get in today electricity in the body, and we'll also talk about neurons and how they operate and how we talk about the electrical properties of neurons. So we've already talked about static electricity a little bit. Static electricity is just the buildup of charges that don't move. So this is in contrast to electricity that might flow through a wire. That would be current, which was already defined. So this is just static. These are charges that build up in an isolated location. All the things that we've talked about here apply already. So when we're talking about static electricity, the buildup of charges, what types of charges are we usually talking about? Positive or negative charges? Negative charges, because negative charges move more readily. So usually when we're talking about these charges, we're talking about negative charges or electrons. Most of the charge on the human body, at least when we're talking about static electricity, are on the skin or hair. So last week or the week before, when I brought the Van de Graaff generator, remember Janelle put her hands on the Van de Graaff generator, I think Kate did it too. That static electricity, all those electrons, they just built up on their skin. They don't actually go into their body, but they build up on their skin and on their hair, of course, and that's what caused their hair to stand up on end. Because you have this buildup of charges, all like charges, negative charges, and they're all repelling from one another. And that causes the hair, for example, when Janelle had her hair standing up, causes those hairs to repel one another and to stand on end. Now, the body is a conductor, and we'll see some applications of that. It conducts electricity differently depending upon what part of the body you're looking at. So the body can conduct electricity. Well, and there are 3 things that affect how it conducts electricity. First of all, what's the property of the body property of the body itself that affects how it conducts electricity. We talked about this in terms of Ohm's law, if you recall. Which one of those properties, Pi or R, is a property of the body and how it conducts electricity? Remember that equation we had, P, I, and R? Which of those refers to some property of the body? V was voltage, I was current, R was resistance. Well, come on, which of those is a property of the body? Come on, this. The resistance, thank you. So the resistance is a property of the body, whereas the voltage and the current is a property of the electric source that's causing the electricity. So the amount of electricity that the body conducts is dependent upon the voltage, depends on the voltage and the resistance, and then the resulting from those, you'll get a certain amount of current, and of course that current is equal to the voltage over the resistance. Remember, resistance is a measure of how the device, your body in this case, resists the flow of electricity. So a higher resistance, if this is really big, that means this is going to be really small. So the bigger the current, of course, the more damaging it can be to the human body. Wet skin, for example, has a much lower resistance than dry skin. So if you have this expression of V over R, if I have a lower resistance here, that means I'm going to have a bigger current. I have a neighbor who's an electrician, and he says that, like electricians used to, they don't do this so much anymore because there are other devices to test circuits, where they would touch their fingers and then they would touch the wires with their wet skin to see if the wire was hot or not. And of course, over many years of doing that, they would lose feeling in their hands because it damages your tissue. But the reason that they would lick their fingers, and I don't recommend that y'all do this, but they would lick their fingers, is to make the resistance of their skin decrease, and it increases the current and allows them to feel it more readily. All right. Let's see. There's a table of currents and their effects on people on page 158 in your book. I'm just going to sort of highlight some of these, but you can follow along if you want, if you like. Most people can feel about 1 milliamp. One milliamp, that's going to be 0.001 amps. And about 100 times that, 100 milliamps, that would be 100 milliamps is 0.01 amps. Actually, I'll just write these in milliamps. I think it'll be easier. Most people can feel 1 milliamp. 100 milliamps will cause fatal defibrillation. Which means what? What does that mean? Fatal fibrillation. Actually, it's fibrillation, not defibrillation. What does that mean? All right, the heart stops. So it's just a fancy way of saying that it causes the heart to stop. 100 milliamps can cause that. 300 milliamps, if you go up by a factor of 3, can cause burns. And when you're actually defibrillating the heart, like those on the movie, clear, right? Y'all seen that? That uses about 6,000 amps. Oh, is that right? That can't be right. Is that what it says?
6,000 million.
6,000 milliamps. Okay, yeah. And so 6,000 milliamps, that's about 6 amps. Gives me, you use this for a defibrillation machine. I've never seen one of those operated. Anybody ever seen one outside of the movies? Have you? Yeah? What's it like? When they, Brent? When they use the defibrillation machine. Is it like in the movies where the people sort of convulse?
Yeah, I've never seen, I mean, I teach lifeguard courses.
Right.
So,
But you train on them.
yeah, we try. I've never actually shot somebody with one.
Oh, okay. Yeah. Well, if you do, let us know. All right. So anyway, 6,000 milliamps with a defibrillation machine. The amount of current that the body receives is heavily dependent upon the path that it takes. So for example, here's a picture of me. I have very large arms. Cauliflower hands. You're going to get different amounts of resistance as electricity flows through you. So for example, if I have really wet hands and I just touch something, a wire, the electricity would just flow between, say, from this finger to this finger. Is that going to be high resistance or low resistance?
Low.
It's going to be very low resistance, especially if the skin is wet. Because whenever your skin is wet, that causes your resistance to drop drastically. However, I have electricity, say, flowing from my hand down to my foot. I'm going to get a much higher resistance. It just has more to go through. It turns out, though, that actually the resistance of the skin is quite a bit different from the resistance of the internal part of your body, and that the resistance of dry skin is quite a bit larger than the resistance of your internal body. This will come up again later today when we talk about body scanning and how to use body scanning to analyze the amount of skeletal mass and muscle mass in your body. And actually, we'll see one of those. The rec center has one. We'll get to see it later. Likewise, it's a lot higher resistance. Say if you have electricity that flows from your hand to your foot versus electricity that flows from a hand to a hand, you'll get a lower resistance just because the path is shorter and there's less stuff for the electricity to flow through. If your electricity flows across here and across your heart, right, then if it goes from your head all the way down to your toes. So you just have different paths through your body through which the electricity can flow, and then it'll get different resistances. Lower resistance means a higher current. A higher resistance means a lower current. Let's see, I have a little video here. This is, I think, like Scientology has been sort of the big thing lately, right? Because there's been various, I don't know, documentaries or whatever. But Scientologists, they use a particular device called an e-meter. You ever heard of this? Have y'all seen any of these shows on the television? No? I'm not sure if there are any Scientologists in the class. If there are, sorry. I don't mean to be offensive. But they use an e-meter, which is basically just a thing that measures the resistance of your body. You have these two metal cans that you hold in your hand, and it puts a very small current through your body, and it measures the resistance of your body. And it's actually pretty effective at figuring out very small changes in your body, like are your palms sweating? If your palm sweats, then it's going to change the resistance of your body. It'll lower the resistance of your body. But it also reacts to internal things in your body. This isn't vetted. Like, people don't really know exactly how this works, but they've used it for 50 years or whatever, as long as this group has been in existence. But I have a little clip here that talks about the e-meter. The e-meter is actually something called a Wheatstone bridge, and a Wheatstone bridge is just a device used to measure resistance. So this was, I think it was from 60 Minutes. Anyway. So there are lots of reasons to run electricity from your body. Like if you're a Scientologist, you can use it to determine these sort of bad thoughts that you might be having. But there are other reasons too, like the defibrillator. And there's also another device called a body scanner. Some of y'all might have seen these before. Let me pull it up here. This is an in-body body scanner. Pull it up in Chrome. You ever seen one of these devices? Yeah, do y'all have one in the athletic training department? It's a thing that you stand on this platform here. And it sends a little current through your body, right? It tells you all kind of stuff about the composition of your body. Do y'all have one? Yeah, there's one in the rec center. You can pay like $10 to get a body scan. And hopefully we'll get to see it next week when we go over there. But basically you stand on, you have to get your socks off, and you stand on these little metal plates, and then you hold these two things, and it runs a current through your body. Now the one that they have is a little bit different from the ones that others have, where they send two different frequencies of current. I'll show you a picture here in just a second how that works. Where based on when they put that current through, say through your feet, and then they measure the current that comes through your hands, they determine what is the resistance of your body. And because you have such a different resistance in, say, your arm than you do in your trunk, then sometimes it's difficult to tell the difference between what your body, how it's composed here, and then your body, how it's composed here. So what they use is they use two different frequencies of electricity, where one of those frequencies will analyze your trunk, sort of the main part of your body, and the other frequency will analyze the appendages. Let's see, I have a figure. I thought I had a figure. Must be here. Oh, here it is. So this just shows different frequencies of electricity. So these orange arrows are high frequency, and the blue arrows are low frequency. And they just take different paths through the body, which means that they assess the scan, or they scan different parts of your body in different ways. So that you're able to get a good measurement of your appendages, and then also of your trunk, your sort of your core, where your organs and what have you are. I'll send y'all this this website, but you might have a basic question on your next exam, and we'll talk more about it when we go over to the rec center next week. So we'll see this a little bit more. I had this done. Let me just sort of show you what the scan looks like. This is kind of personal, because it like has all my business on it. And look, it even has a picture of me right there. But so this is, it gives you a whole bunch of stuff. It tells you your body water. Zoom in a little bit. So it tells you how much mass you have of body water, how much of dry lean mass, body fat mass, and then this is your lean body mass. And then they put it all together and they give your total weight. So it also tells you sort of your skeletal mass and whether it's sort of where it's supposed to be. So here I have sort of normal muscle mass in my arms and in my trunk, but my legs are over, so I have too much muscle mass in my legs, because I cycle a lot, right? And so I just sort of build up that extra muscle mass. But I've been lifting weights all semester just for this, so that I can do another body scan, and I'm hoping that they'll come more in line, because you want your whole body to be normal. So we'll see what happens with that. We'll do another scan and we can look at the results. I know I've gained 10 pounds, so that's a good thing, I think, right? Yes. Okay, so we'll see how that goes. Also, we can see how it affects my BMR, because remember we talked about BMR? This is my BMR. It's about 1,700 kilocalories. So that's what I need to eat every day just to maintain basic living. All right, and then above that, if I have any activity, I'll need to eat additional food. So we'll see this. Hopefully they'll be able to do that for us, and they have that as a service for the students as well. All right. So let me just put some of that in words. The E-meter measures the resistance of your body. this changes based on anxiety or other thoughts, or say anxious thoughts. Very minute things like sweat on your palms, but also other things like muscles tensing or just a physiological change in your body. So sweat on your palms, muscles tensing, or other physiological changes. All right, so that's the E meter, and it can sense these changes when you wouldn't otherwise sense them. So you saw the lady, like she didn't think that she was changing in any way, but just the thought of these things would actually cause a change in the resistance of her body. And Scientology, like, they take that and they sort of make a whole theology out of it. Now, also the body scanner, and the one that we'll see is called a direct segmental multi-frequency bioimpedance analysis. Those are a lot of words, but they have certain meanings that we've already talked about. Segmental just means that it can analyze the separate parts of your body or the segments of your body, the trunk of your body, and the appendages, legs and arms. So it can analyze those separately, and other body scanners that don't have this segmental portion where they actually have the multiple frequencies are not able to do that. So that segmental comes about because it's multi-frequency. All right. So since the resistance of trunk and appendages is different, they use two frequencies to analyze each separately. All right, so one of those frequencies will assess your core, or your trunk of your body, and then the other frequencies will assess your arms and your legs. So multiple frequency, and then of course bioimpedance. What is impedance? That's just a fancy word for what? What does it mean to impede something? What does the word impede mean? Or more importantly, what is it a synonym for? What does impede mean? When you use the word impede, how do you use it? You use the word impede ever? Slow down. To slow down, right. And that's just a synonym then for what word that we've been using. Resistance, right. So impedance is just another word for resistance. So this bioimpedance just means the resistance of the body. All right. Be prepared to answer just some basic questions about what this body scanner does and how it does it, and sort of the information that you get from it. We'll come back to that next week as well when we go over to the rec center. All right. Let's look at the nervous system. Can I go down from here, y'all? No? Go back. Yeah. All right. So for the nervous system uses cells to transmit information through the flow of electric charge. And we'll look at how this charge actually travels along our neurons. Oh, that's a B. We'll look at how this works, sort of some of the basics of how this charge is transferred from one part to another. So this occurs in response to stimuli. So for example, if I pinch myself, I feel that and I'll react to it. Or if I burn my hand, I'll feel that and react to it even more quickly. This stimuli affects our body in some way, and then these charges are moved through the nervous system. There are three different purposes of the nervous system. The first is for sensory input. So this includes both internal and external stimuli. This is just from the environment around you, somebody pinching you or whatever. And then internal stimuli from the organs. Or from other body systems. We've seen this already, right? Sort of various times throughout the semester. For example, when you get too hot, right? There's a signal that's sent to your brain to produce certain chemicals to help you cool down. So there's all sorts of communications internally within your body through the nervous system. The other purpose of the nervous system is integration. This just processes the sensory input. It's like the CPU of your computer. Processes the sensory input and determines what to do in response. You know, that could be sort of a higher level thing where, I don't know, my girlfriend or whatever says that I look goofy, right? And then I determine what to do in response. Or something more visceral, like I burn my hand and I jerk it back. Right? Something that requires thought, or just something that occurs without you really thinking about it. But this integration occurs, it processes this sensory input. This is called our central nervous system, or the purpose of our central nervous system. And third is motor output. And so the nervous system causes the body to respond. And this is something called the peripheral nervous system. Alright, so it just causes you to move your muscles or do whatever it is in response to the stimuli. So you have these three purposes of the nervous system. Sensory input, it just takes the input from the various senses, either from external or internal stimuli. Integration, it actually processes that input, and then the response is through the peripheral nervous system, or the PNS, which is just the motor output. And then we have, as we've already said, we have two main parts of this nervous system, the central nervous system and the peripheral nervous system. The first part is the central nervous system. This includes the brain and the spinal cord. you need to know what it does, and that is that it integrates the information from the peripheral nervous system or from these external stimuli, which we've already said. And then the peripheral nervous system, this includes everything else. Or at least the rest of the nervous system. So all the neurons that are in your body that act, they receive and send information to the central nervous system, either the brain or the spinal cord, or through the brain and the spinal cord. Okay, and within the nervous system, we're going to talk a bit about neurons and how they work. But we have two types of nerve tissue. Neurons. The first one is neurons, which we'll get into quite a bit. So I'll just list it there as neurons. But then the second part are just support cells. The neurons, they'll actually transmit electrical signals, and we'll see how that happens. But the support cells just help this to occur. So they provide various roles of support. We're not going to talk about them too much, but we'll see sort of them in passing. Y'all seen neurons before? Some of you have. So like the myelin sheath, for example, is one of those support cells. We'll see that as well. But other cells in the nervous system that provide some sort of support. So we're just going to look at the neurons because that's where sort of the physics comes in. Though the myelin sheaths, for example, also provide a pretty important role. Let's look at neurons. They have two main parts. A cell body, or three main parts. They consist of a cell body. That's sort of the main part of the neuron. I'll show you a picture in just a second, although there's also a picture in your book. Dendrites and axons. Oh, there should be an R there. All right, the cell body is the main part of the neuron. And it basically controls everything that goes on. So it controls the flow of electricity. And then the dendrites and the axons, they act as sort of paths over which these electrical signals are sent. Dendrites will receive input signals. And axons will transmit the signal to the next neuron. Actually, to the dendrite of the next neuron. So each of these cells within the nervous system, these neurons, they will actually see a much longer string, and so each one will convey the electrical signal along from the dendrite to the axon and onto the next dendrite through the axon and on and on. Let's see, I have a picture here. I'm sorry, I want to save these for just a minute. Well, let's see, I'll go ahead and pull it up. Okay, yeah, so here's a picture. We'll come back to this figure soon. Don't worry about the bottom part. But this is our cell body. What are these parts called? These are the dendrites, very good. And this part are the axons. So the dendrites receive the signal, goes to the cell body, and then that electrical signal is sent on to the next cell through the axon. And they call the synapses are the connections between the neurons. You have a little video. It's on YouTube. You ever watch the 2-minute neuroscience? It's kind of like the Minute Physics series on YouTube, but it's about neuroscience. And I guess neuroscience is more complicated than physics, so it's 2 minutes instead of 1. But they have a series of nice little videos on neurons and how they work. Let's watch this one. This is just sort of their overarching video on the neuron. I suspect many of you have already known this, but you need to know the basic parts of the neuron, the dendrite, the axon, and the cell body, and how they work, the basic functions that they provide. I think that most of you know that. Most of you have it. Okay, so the neuron has three different classes, of neurons. You have sensory neurons, motor neurons, and interneurons. We sort of dealt with these before when we were talking about the different parts of the nervous system. The sensory neurons conduct input signals. To the central nervous system. And these are responsible for our 5 senses. The motor neurons conduct the central nervous system signals to the effector organs. What are effector organs? What does that mean? If I want to make some change, what is it? Like, for example, if I put my hand on a hot stove, what is the effector organ that's going to be, that you'll send the signal to? Right, to the muscles. So this includes muscles and glands. And then the interneurons, these are just in between the sensory and motor neurons. Alright, let's talk about membrane potential and then action potential. And I go down from here, y'all? So these are the 3 different classes of neurons: sensory, motor, and interneurons. I'll wait just a second. Oh, synapses? That just means when you have connections between the neurons. Alright, there's a figure in your book that goes into this membrane potential. We'll talk about the membrane potential. That is sort of what is the resting potential of in your cell and these neurons. And it turns out that the resting potential is that the inside of the cell is a negative potential, and that the outside of the cell is a positive potential. And we'll get a little bit into sort of why that occurs. It's because of the chemical gradient of the sodium and the potassium ions that are at play. And then also the electrical gradient, because when you have these different charges inside and outside of the cell, then they'll be attracted to one part or the other. And then they have this other thing that I don't know much about, this pump, this sodium potassium pump, which y'all probably know more than I do. Y'all probably know more than me about all this stuff, actually. So let's see, there's a figure on page 163. So I have this cell membrane. You can sort of think of it as a cylinder. this outside part is our cell membrane. And on the outside, I have sodium ions, I have chlorine ions. What are these called, by the way? The positive ones are called what? Cations, and the negative ones are anions, right? And on the inside, I have potassium ions. Those are cations. And then I also have some other negative ions. These are just big organic molecules, and they don't really move around that much. So these are all separated by the cell membrane. You have these on the inside and these on the outside. There are more potassium ions on the outside than the inside. Or excuse me, more potassium ion on the inside than outside. So by diffusion, you'll have potassium ions that will move from the inside to the outside. Diffusion is just this process where these ions can move through this cell membrane. So by diffusion, these potassium ions will move outside. And in a similar way, the sodium ions will move inside the cell membrane. We would talk about this because it's a chemical gradient. That if I tend to have more of one substance, if I have more potassium here than I have here, we will tend to have this potassium move to the outer part until it's equalized. So you get equal amounts on either side. And likewise with the sodium, they'll tend to move inside the cell membrane until this is equalized. So that's a type of a chemical gradient. However, the cell membrane, the permeability of it is such that more potassium ions move out than sodium ions move in. Right. The net result of that, if I have these potassium ions moving out, and then I have these sodium ions moving in, if I have more potassium ions moving out than the sodium ions moving in, just because of the cell membrane, the permeability of it, what effect will that have on the potential or the net charge inside of the cell membrane? Will the net charge inside the cell membrane be positive or negative? I got these positive charges going out, the potassiums are going out, the sodium charges are coming in, and they're replacing them, but these potassium charges are moving out at a larger rate. So will the inside of the cell body, will it be positively or negatively charged? It's going to be negatively charged, right? Because I'm getting rid of these positive charges and I'm replacing them, but I'm not replacing them at the same rate. So the net effect of that is that I get a negatively charged cell body. So I get a negative potential. That's not the only thing that's going on. There are actually a couple different things that are going on. You can think of it in three different mechanisms. There are three mechanisms at work that cause this negative potential inside of the cell body. Let me write that. I get a negative potential inside the cell body. These three mechanisms are a chemical gradient, I also get an electrical gradient set up. And then the third thing, and your book talks about this a little bit you also have a sodium-potassium pump. This causes the potassiums to come in and the sodiums to go out. But the net result of these, the net result is a resting potential of about minus 70 millivolts. Right, so that's sort of the equilibrium position for your neurons. They're always, unless they're working and sending some signal, they're always have this potential inside of them of about negative 70 millivolts. I have another little video from this 2-minute neuroscience. Can I come away from this? It talks about this this potential, the membrane potential it's called, and there's a whole section in your book, but I thought this did a nice summary of what's in your book. Can I come away? No? Let's see, I'm going to stop.